Hi guys, today we're going to talk about light flickering in videos. Why does this happen? And how can we fix it? Let's go. Sometimes we record a video using artificial lighting, and then we notice that the lights are flickering, which was not intended. Notice that this doesn't happen when using natural light, as we are now. But why does this happen and how can we prevent it? The explanation is rather complex, but I'll try to keep it as digestible as possible. Lights powered directly from the electrical outlet operate on alternating current, or AC. That's the graph we're seeing in the screen. The current is said to be alternating because its direction of the electrons changes over time, causing the voltage and current values to oscillate between positive and negative, depending on the direction of the electrons. As such, the value of voltage and current in AC is always fluctuating and is never constant. This is what causes the lights to turn on or off or flicker. Our eyes don't notice this because the frequency in which the light turns on and off is very fast, giving the illusion that it is constantly on, although this is not true. And we can see this in the graph here. So we start the alternate current cycle with the light turn off, okay, and then we start rising the voltage and current, okay. The light starts to become brighter and brighter until it reaches the max intensity, okay. This is the max voltage and current point, okay. After that it starts dropping, the light starts to dim, to dim, to dim. It reaches zero, the light is completely off, and now we're going on negative territory in terms of voltage and current values, okay? But in terms of light intensity, it's exactly the same whether we're using positive or negative values of voltage or current, okay? The only thing that matters is that electrons are going through it. And now the light becomes more intense, brighter, and it reaches the max intensity level here on the negative side, which is exactly the symmetrical value of the positive side, okay? So it's the same intensity, only on the negative side, but in terms of light intensity is exactly the same, okay? After that, the light starts to get dimmer and dimmer and dimmer, and it switches completely off, and that's the end of a cycle. And then it repeats again over and over again. There are also battery-powered lights which run on direct current, or DC. The current is said to be direct because the direction of the electrons never changes over time, meaning that the voltage and current values are never negative, but always positive. The most common form of DC is provided by batteries. Okay, it's a constant value of voltage and current over time, causing the lights that are powered by these batteries not to flicker. And what if I use LED lights plugged into an AC outlet? Doesn't that solve the flickering problem? Unfortunately, no. For now, LEDs only work with DC, and as such they need a device called LED driver when they have to be plugged into the AC outlet. The LED driver is responsible for the conversion from AC to DC power, but depending on the quality of the driver, we may not get constant DC power, but something called pulsating DC, which we can see here in the graph. Meaning that although it does not change direction, it does vary its intensity over time, which means that in this case the LEDs will also flicker. Okay, we can see that although this red line over here, the pulsating DC, which is the output of a low quality LED driver, okay, because it should be able to output constant DC. In this case, the pulsating DC, it's DC because it's never negative, okay, it's always positive, so the electrons continue to flow over time only in one direction, but its intensity in terms of light, which corresponds to voltage and current directly, oscillates. You can have an LED that goes back and forth between medium and high intensity, which in practice means flicker. So in short, if you have a light connected to the AC socket, even if it's an LED light, you may encounter light flicker in your videos. So, as we already know, alternating current varies the direction of energy flow over time, and this happens so quickly that our eyes don't even notice it. But how quickly? In fact, this happens dozens of times per second, depending on the country we are in. In the case of European countries, for example, among others, electricity operates at 50 cycles per second, or 50 Hz. In other countries, such as the USA, electricity works at 60 cycles per second, or 60 Hz. Each cycle has two changes of flow direction, okay, which corresponds to two power peaks, one in each direction, okay? So it's this one over here on top, on the positive end, and this over here on the negative end. Both of them cause the lamp to light up, which means that a lamp will turn on and off twice in one cycle, meaning 100 times per second in countries with electricity at 50 Hz, such as Portugal, or 120 times per second in countries with electricity at 60 Hz, such as the USA. It is also because of the synchronization issue that most countries with 50 Hz electricity use the PAL video system, which uses frame rates of which 100 Hz is multiple of. For example, 25 frames per second, 50 frames per second, and 100 frames per second. And most countries with electricity at 60 Hz use the NTSC video system, which uses frame rates of which 120 Hz is multiple of. For example, 24 frames per second, 30, 60, and 120 frames per second. Although in general this was the rule, there are exceptions. For example, Brazil, our brother country, uses the PAL system, but has electricity at 60 Hz. These video systems were developed for analog color TV broadcasting, and as a curiosity, there is also a third system, CCAM, but most of the countries that use it have already converted to the PAL system. Oh, by the way, to be more precise, NTSC actually uses 29.97 frames per second and 59.94 frames per second, but it's common to see these values rounded up to 30 and 60 for the sake of practicality. As we already know, the frequency of the AC cycle is fast enough for the human eye not to notice, which gives us the impression that an AC light is continually on, although this is not true. However, our camera sensor is fast enough to be able to capture multiple frames in the middle of the electrical cycle, where the intensity of the light is not constant from frame to frame. In some frames the light is on, in others it is off, and in others somewhere in between, which causes the lights to flicker in our videos. To better understand how we can solve this issue, let's explore some scenarios in more detail, roughly calculating the amount of light the sensor captures in each frame, which corresponds to the exposure. In these examples we will use 50 Hz electricity, but the logic is exactly the same for 60 Hz. As we already know, the AC graph, currently in the screen, represents the variation of voltage and current over time, which causes an AC light to turn on and off depending on the line of the graph. This means that the amount of light emitted increases or decreases depending on that line. As such, to get an idea of the total amount of light emitted during a given time interval, we can calculate the area between the line and the time axis, in yellow over there. The larger the area, the greater the amount of light emitted, and the greater the amount of light that hits our camera sensor, meaning a higher exposure. In order not to have flickering lights in our videos, our goal is that the exposure remains constant over time, meaning throughout the various frames of the video. This means that we have to be able to synchronize our sensor with the electrical frequency so that the area of the graph, meaning exposure, is constant. In the case of 50 Hz, the minimum value where the area remains constant is 1/100th of a second or half a cycle, as we will confirm next. We'll come back to this value again later on when we talk about slow motion videos. In order to simplify area calculations and not to have to use integrals or integral calculus to calculate the area of curved continuous functions, such as trigonometric ones, in this case it's the sine function, okay, in the particular case of the alternating current, let's make an approximation to the curve using rectangles and triangles, where the area is simpler to calculate, and for our purposes it fits perfectly. So let's assume that a right triangle has an area x and therefore represents luminosity x or exposure x. With two right triangles together, we get a rectangle with twice its area, or 2x. And if we join these two rectangulars into a larger rectangle, it will have twice that area, meaning 4x. With these blocks, we can make an approximation to the curve, as we are seeing here in the screen, getting approximately an area of 12x of luminosity or exposure for half a cycle, or 24x for a full cycle. Note that although the area is negative at the bottom of the graph due to the opposite direction of the electrons, this does not impact light emission, which is equal to the positive part of the graph. This is why we have two light peaks for each cycle. If this wasn't the case, we would have zero exposure over the course of a cycle instead of 24x, because the positive area would cancel out the negative area. That's not the case. We in fact have 24x of exposure in a single cycle. So going back to our question of sensor and electrical frequency alignment, and assuming that the lens aperture and sensor sensitivity, or ISO, remain constant throughout the video, we are left with two controls to control exposure: frame rate and shutter speed. Frame rate defines how many frames per second the sensor captures to create the video, and shutter speed determines how long the sensor is exposed in each frame. Note that, except for artistic reasons, it doesn't make sense to have the shutter speed slower than the frame rate. For example, if you're capturing 30 frames per second, you should be using a maximum shutter speed of 1/30th of a second. Otherwise, light from one frame leaks into the next, creating blurry videos. So let's start with the simplest synchronization of all, frame rate. If we align the frame rate with the electrical frequency, we'll never have flickering lights in our videos. That's it. Let's look at the first example here in the screen, where we're using 50 frames per second with a shutter speed of 1/50th of a second, so that light is captured for the entire duration of the frame. In this case, we have a constant 24x exposure on every frame of the video. What if we start recording in the middle point of the energy cycle, somewhere in between start and finish? No problem, okay? And we're going to look at that right now, because the area remains the same. The area of light that is captured remains the same regardless of the starting point where we start recording, okay? As you can see, there is no problem whatsoever. We have constant 24x exposure in all video frames. What if we use a different shutter speed? One that isn't even compatible with the 50 Hz family, like 1/80th of a second? No problem, because the amount of light, as we're seeing right now, the amount of light captured is always the same across frames, given that the capture always starts and ends at the same point in the wave. This is true for any shutter speed value, as we can see here, we have constant 16x exposure in every video frame, okay? It's less light than 24x exposure because we are limiting the amount of light because we have a faster shutter speed, 1/80th of a second in this case. Notice that I mentioned shutter speeds compatible with 50 Hz. Probably many of you with experience in video already know what I'm referring to, but I think it's important to clarify this issue. Compatibility in this context means the ability to eliminate flickering lights, and it's applicable to both frame rates and shutter speeds because they both affect exposure in the same way, by controlling the timing of the exposure in a frame. Note that shutter speed can only shorten the exposure time that is already preset by the frame rate. So both control the exposure time of a frame in practice. In the case of electricity at 50 Hz, we have 2 light peaks per cycle, meaning the light peaks have a frequency of 100 Hz. And as we already seen, this frequency also corresponds to the minimum time needed to get a constant exposure, which is 1/100th of a second, or half a cycle. And I'll explain this part better when we talk about slow motion. However, if we add more half cycles to the exposure, we always maintain a constant exposure value with an intensity that is multiple of the initial 1/100th of a second. This tells us that, in fact, any multiple of 100th guarantees us constant exposure. If we take 100 and divide it by integer values, we find the multiples of 100, of which we are only interested in the integers, which are the ones that are present in most cameras. 100 divided by 2 is 50, 100 divided by 3 is 33.3333, which is not an integer value, but a repeating decimal, so that doesn't count. 100 divided by 4 is 25, 100 divided by 5 is 20, and so on. As it is not usual to shoot below 24 frames per second, we will stick with the values 100, 50, and 25. These values are the frame rate and shutter speed values compatible with 50 Hz electricity. You can do the exact same calculation for 60 Hz electricity, getting the various multiples of 120 more or equal than 24, meaning 120, 60, 40, 30, and 24. We usually don't shoot at 40 frames per second, so 40 is out of the equation for this. Notice that, as we already seen before, these values align perfectly with those used by PAL standards for 50 Hz and NTSC values for 60 Hz. Now you know why. Now let's assume that for creative reasons, for example, we want to use frame rates that are not compatible with our electrical frequency. For example, if you want to use 60 frames per second in a 50 Hz country, like Portugal, you can't maintain a constant exposure in the video by using frame rate alone. And that is exactly what we have here in the screen, okay? So this is a 60 frames per second example, okay, 3 frames. And I'm using 1/60th of a second shutter speed, meaning that I have full frame exposure. And in the first frame, if I add up all the X's, the yellow X's, okay, to try and understand what kind of exposure I have in the first frame, which stops at the red line over here, I get about 21.5x of exposure in the first frame. In the second frame, between the first and second red lines, I have 17x of exposure, so it's lower. And in the third frame, between the second and the third red lines, I have 20.5x of exposure. So different values of exposure for each frame. This unfortunately means the lights will flicker in the video. Okay, so to address that, in this case, we have to use shutter speed to be able to adjust the exposure so that it is compatible with the electrical frequency. So let's choose a shutter speed compatible with 50 Hz and higher than the frame rate we choose to shoot, so that we don't have blur in the video, as we already talked about. So in this case, the shutter speed above 60 frames per second and compatible with 50 Hertz is 1/100th of a second. So if we apply this time limit to the exposure of each frame, okay, so I'm just exposing the sensor in the frame by 1/100th of a second. Okay, the remaining time of the frame, the shutter is closed, so no light is hitting the sensor. So by applying this time limit to the exposure of each frame, this ensures that it remains constant throughout the various frames, even with a frame rate that is not compatible with our electrical frequency. And we can see that over here. So I have less exposure, of course, because I'm capturing less light this time, so only 12x, but the exposure along the frames is exactly the same, so I have constant exposure now, meaning the lights won't flicker, and that's exactly what I was intending to do. And what about if I cannot exactly start capturing the video at exactly the right time of the wave? No problem, okay? I can start recording in any point of the wave. The exposure will still be consistent along the frames, and it will be exactly the same. As you can see, I start a little bit offset from the start of the wave. The exposure remains constant along the frames, 12x, 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 and if I start a little bit to the right, still the same exposure in each and every frame. And what about slow motion? To shoot in slow motion, you basically increase the frame rate of the recording and then slow it down in post-production. For example, we can shoot at 100 frames per second and then play the video back at 25 frames per second at 1/4 speed, for example, thus giving us the visual aesthetics of slow motion. And what about shooting above 100 frames per second? Can we shoot without flickering lights? Unfortunately, no. 100 frames per second is the maximum frame rate limit with no flickering lights, using electricity at 50 Hertz, because 1/100th of a second, or half a cycle, is the minimum range where we can guarantee constant exposure in all frames, as we've already seen. In the case of electricity at 60 Hertz, the maximum is 120 frames per second. As we can see here, at 100 frames per second, okay, I have constant 12x exposure no matter where I start recording in the wave, okay? I can start a little bit after the wave has already begun, no problem. I still have 12x exposure, and even further, I still have 12x exposure no matter where I start recording in the wave. Now, let's look at an example with, for instance, double the frame rate, or 200 frames per second, which even seems to be a compatible value, right? Because it's double 100. However, here it is. As soon as we start shifting the starting point of recording on the wave, we notice that the frames capture different exposures, causing the lights to flicker in the video. It's for this reason that 100 frames per second is the maximum frame rate limit for AC-powered artificial lighting at 50 Hz. As we can see here in the graph, using 200 frames per second at 1/200th of a second, so it's the maximum exposure I can have without having a blurred video. I have the first frame exposure at 8.5x approximately, the second one 3.5x, then 8.5x, then 3.5x. So I don't have a constant exposure along the frames, meaning the lights will flicker. Therefore, for frame rates above 100 frames per second, the only option you have is using natural light or DC powered lights, either via battery or good AC to DC converters, to ensure that the output is not pulsating DC, as we've seen when we talked about the LEDs, remember? So in summary, to align our camera sensor so that we don't have flickering AC lights, we must use frame rate or shutter speed values of which the frequency of the flickering lights is multiple. These frequencies are 100 Hz for 50 Hz electricity and 120 Hz for 60 Hz electricity. If you choose to align the frame rate, you don't need to worry about shutter speed. Don't forget that the maximum frame rate is 100 FPS or 120 FPS, depending on the electrical frequency. If, for creative reasons, you want to choose a frame rate that is incompatible with the electrical frequency, you will have to choose a shutter speed that is compatible. Don't forget that the maximum shutter speed is 1/100th of a second or 1/120th of a second, depending on the electrical frequency. Finally, don't forget that in any of these scenarios, and except for creative reasons, you should always use a shutter speed equal to or higher than the frame rate, in order to ensure that you don't have blurred videos. And that's it. I hope this was useful to you. Please leave your feedback and share your ideas and opinions in the comments. And if you want to stay up to date with the latest videos, you can subscribe the channel and click the like button. Thank you, and I'll see you next time.